Okay, so welcome to week 5 of Specialist Maths, and as you can see, week 5 is all about vector functions, and we're building on both the calculus knowledge that you have and also the vector knowledge that you have from Unit 3. So we're going to just review a little bit about vectors from the beginning of the year, just very quickly, and talk about the components of vectors. So vectors are really super handy because they let us continue our study of motion both in 2D and 3D. So we've already looked at the 2D motions travelling in a straight line. We can apply vectors to this as well, but the beauty of vectors, we can apply it to the 3D motion. Because if you recall from Unit 3, vector quantities have not only a scalar quantity, they've got direction and magnitude. If the motion is in a straight line, as we've done before in the previous couple of weeks, we don't need to use vectors, so we can just use scalars in the equations. That's okay if it's the straight line motion, but that's not always the case, so we need to extend our mathematics to cover the 3D motion. So welcome Harrison and Tyson, I hope you can hear me. So from Unit 3, these are what the vectors looked like. We had a vector A, I can't show the tildes here, but a vector A defined in 3 different directions, the I, the J and the K direction, with a quantity in each direction making up the vector. Now this is a static point with no motion. Okay, so this vector is a static vector and it just extends into space. And from the origin to the point 3, 4, negative 2 in 3D. When we have vector functions, we can introduce for each I, J, K component can be represented by a function of time. So for example, this is a vector as a function of time, a vector that changes over time, and you can see the I component is t plus 1 and the J component is 3t, where t is time and time is greater than or equal to 0. So this allows us to describe the motion of this particle in detail with respect to time. So all we have to do is substitute different times into this vector function, and we can evaluate the position at that particular time, so that we can use that to describe the motion of a particle in both 2D and 3D. So if you recall, this is the conventional way of representing three-dimensional space. So we have, this is the I direction, goes in the x-axis, the J direction goes in the y-axis, and in the z-axis, the third dimension, we have the K component. So that's just recalling stuff from Unit 3. So we can have a particle moving in 2D on a plane. Okay, so this is just on the xy plane. We can define functions. X is a function of t and y is a function of t, and this particle is moving as a function of time, and the x and the y act independently, and they're both functions of time. And then we can of course extend this to 3D by introducing the third component k. So what does this actually look like? So what we can actually do, this is a 2D simulation. At various points in time, the vector is moving through space, right? This object, if it's defined by this vector, is moving through space, and we can see where it is at any time. So here it is at time equals, I don't know, 15, whatever. Could be here. And then at time equals 25, it could be here. So the vectors give us a notion of the direction with respect to time, and also once we know the position at different times, we can establish the direction of the motion. So this object is moving in general in this direction. So we can put an arrow on its trajectory to say which way it's moving, and and here it is when at t equals 0. It starts at this point, not necessarily at the origin, but somewhere here. So this object starts at t equals 0 and moves in this kind of parabolic arc, and then maybe hits the ground here. Okay, so this is stuff you know. So recalling back to Unit 3, the addition of vectors. Okay, this works the same way even when they're a function of time. So you've got your plane velocity is a vector quantity, it's got direction, you've got your wind velocity. So this is a tailwind pushing this plane to go even faster. So the resultant velocity, just add them up. And thinking about what's happening even when the vector is a function of time, these attributes still apply. So we've got a headwind here this time, so that's going to diminish the resultant velocity, is going to be smaller of this aircraft. And then maybe we've got a velocity coming from the side here. Adding the velocity vectors together, we have a resultant velocity for the aircraft in that darker blue colour. Okay. So any vector equation made up of independent components as functions of time can be converted to a Cartesian form equation. So if for some reason you need to do that, you've got a vector function equation dependent on time here, where the I component is a function of time 2 minus t, and the j component is a function of time 3 plus t squared. So to turn this into a Cartesian equation, you just simply equate the I component with the x variable, because that is defining the x coordinates of that the path of that object, and the y coordinates are defined by the j component, which is 3 plus t squared. So there's lots of different ways you can do that. You can rearrange this equation, so you've got t is equal to 2 minus x, and then you can just simply substitute that into the equation here, and you've got a Cartesian form of the same equation. Okay, and you simplify it, and there you have a parabola. So, so this parabola is the Cartesian form of this vector equation. But there are some things you need to remember. When you're dealing with motion, time is always greater than or equal to 0. So this path is restricted in its domain and range because of the t variable with the time variable. So at t is equal to 0, x is going to be equal to 2, and y is going to be equal to 3. And this is actually the starting position of this path here. So, 2 and 3, 2 and 3. So this object is going to start here. At t equals 0, it's going to be there. And then it's going to go off in its parabolic path following this rule. Okay? It doesn't exist before t equals 0. So this is going to restrict the domain, so it has to be, the domain is going to be x is greater than or equal to 2, and the range is going to be y is greater than or equal to 3, because it doesn't actually exist before those values of x and y. So that's really important. Okay, so you can have any function of t representing the I component or the j component, so they can be trig functions as well. So the important thing is when they're trig functions, you can apply all those lovely identities that we've learnt about and complex compound angle formulas that we've learnt about to help you turn these ones into Cartesian equations. So again, we've got x is equal to the I component, y is equal to the j component, and then these two can be related together using the Pythagorean identity, And you can see if you do that, you end up with a circle, which is kind of wonderful. So this vector, like if you substitute t is equal to 0 in here, so for example, r of 0 is going to be equal to cosine of 0 I plus sine of 0j. So this is going to inform us whereabouts this path is starting. So where is it starting? What's cosine of 0? Cosine of 0 is... And what's sine of 0? This is the x and the y. Yep. So this object has the x value is going to be equal to 1. So it's starting here. That's where it's starting. Its path is starting right there. Okay, let's put in some other values in here. Let's put in pi on 4. Okay, so when we put in pi on 4, where is this object going to be? It's going to be at cos pi on 4. This times t is equal to pi on 4, I, plus sine pi on 4, j. So where's that going to be? Which quadrant is that going to be? It's going to be equal to 1 on root 2i, remembering your exact values, plus 1 on root 2j. It's going to be over here somewhere. This is at t equals pi on 4. So just by generating those 2 points, we've got information about the direction that this object is moving in. If you can draw a circle better than me, this object is going to be following the unit circle Cartesian equation path, starting from this point here and going in an anti-clockwise direction. Okay, so that's the extra information that we're given by a vector function. So it tells us the direction of travel, whereas the Cartesian equation on its own tells us the path, but it doesn't tell us where the object is on the path at any time. This equation here, we've lost the t information for, if we're just looking at that itself. But if we've got it together with the original vector equation, we're okay, we can still work that out. Okay. So we know from the unit circle that the domain and the range are restricted to these values, and even if we substitute, if we take t is assumed to be greater than or equal to 0, if we substitute all values of t that are greater than or equal to 0 into the vector equation, this domain and range will also be true for this case. Okay. What about if I do this? The vector equation now is cosine of 3t I and sine of 3tj. Does this travel the same path? And is it faster or slower than the previous vector equation? I require you to do a bit of thinking now. What is your answer? Same path but faster, you think. What do the rest of you think? It is the same path, because if you replace x, if you make x equal to cosine of 3t and y equal to sine of 3t, right, if you do that, you can combine them again using that Pythagorean identity to get the unit circle. That will still be the unit circle. What about if I put in now, into this new version, if I put in r of pi on 12? Where is this particular projectile or object going to be at t equals pi on 12? T equals pi on 12, it's going to be same as the one same place. It's going to be cosine of 3 pi on 12. Right, yep. Of I plus sine of 3 pi on 12j. The radius is the same, but it's actually moving quicker because t pi on 12 is a smaller unit of time than pi on 4 up here. So it's getting to that position, this position. The second one is getting to this position a lot faster. So this object is moving faster. So you're right, Harrison. It is going faster. Okay, so that's another benefit of having the time there. We can work out velocity as well as the direction of travel and the path it's travelling on. So there's a lot of information there. Okay, so if we're given a particle travels on this path, just the circular equation, we don't know the position on the path at any time. We don't know that. And we don't know the direction. And we don't know the starting point. So just a Cartesian equation defining the path is not enough to have all these other bits of information. And particles can travel on the same path at different rates, as we just saw in the example before. And they can be travelling on the same path from different directions. One can be going clockwise and the other one can be going anti-clockwise. And if we don't have the time parameter, we won't know how the object is behaving on that path. Okay. So we're coming to part 2. We're going to just look at those vector components now as a function of time in more detail, because once we have these vector components as a function of time, we can work out, is it possible for these particles to collide? Now, two objects can travel the same path and not necessarily collide. The definition of collision is they're at the same point in time, at the same time. That's what they have to work out. So given two particles A and B, is it possible for these particles to collide? Okay, so the method we're going to use for this is we're going to turn them into Cartesian equations, because it's kind of, we could actually equate them here. We could actually equate the x components and the y components, or the I components and the j components, and solve those simultaneously. That'll work. That'll work too. But you know, we want to work out, do they actually exist at the same place at the same time for the collision to happen? So let's just do that. So we've got the oh yes, we're going to turn it into a Cartesian equation. Okay, let's do that first. So we can turn it into a Cartesian equation. So we're going to end up with this being the Cartesian equation for particle A, which is a parabola and turning point form. So it's got turning point at -3 and 10. Okay, and then we've got the second equation, equation B. The x particles are the x components are the x coordinates are the I components, and the y coordinates are the j components. Okay, so we can turn that into a Cartesian equation, which is a line. And that is, they definitely know if you've got a parabola here that goes like this, and a line, well, you can work out they may or may not coincide, or they may or may not cross. They might cross once. There's a couple of different ways, but you can work it out. There we go. They cross 2 times. There you go. I already had a graph. So they actually cross at 2 points. If you graph these, there's two intersections of the Cartesian equation. But they don't necessarily, not necessarily there at the same time. Oh, you're asking me about the pool room. Was that the one before? Haha, yeah. That's cute, that cat, isn't it? No, we don't have a pool room, unfortunately. So we can actually solve those simultaneously. We can use the CAS or other methods to solve them simultaneously. And we've got two intercepts there. We've got one intercept at 7:35 and the other intercept just from the Cartesian equation at 1591. Now, are these objects there? Will they collide? Are they there simultaneously? They have to be there at the same time for a collision to occur. Oh, there we go. Isn't that cat thing so cute? So we need to determine if they actually collide. So the best way to do it is to equate the x and y components and see if it's possible simultaneously to find a result for t that's true for both particles. So we're going to, if we do that, we've got x 2t minus 3 from particle A equals t plus 2 for the I. This is the I component here. So equating those, solve for t, we get t equals 5. And then we can equate the y coordinates. They're t squared plus 10 equals 7t. Solve that, we're going to get 5 or 2. So obviously, this is only going to be in the same place when t is equal to 5. So at t equals 5, particle A, substituting t equals 5 into that vector equation, gives us 7i plus 35j, and substituting t equals 5 into particle B's equation, vector equation, gives us the same vector. Hooray! So they're identical, so that means at t equals 5, they're in the same place at the same time, so they will collide. You can also work out other things. How far apart they are at certain times. So if you're asked to work out how far apart they are at t equals 1, all you need to do is substitute t equals 1 into each of the equation for particle A and particle B, and then you have two simple vectors that are not functions of time relating to position, and you can just simply use Pythagoras' theorem to work out how far apart they are. And you can also work out if the distance apart is getting greater and greater, because you can actually work this out at t equals 2. So you can determine if they're getting further apart or closer together, depending on the distance between the two objects. Okay, so just generalizing this and relating it all back to calculus. So you've seen our vector equation relating to positions. We've got the I component is a function of time, the j component is a function of time, the k component is a function of time. Okay, so if we have a vector equation defining position, all we have to do to work out the velocity of that vector is take the derivative of it with respect to time. Now the notation you might see for this might be r with a little dot on the top. That's the first derivative with respect to time. And to do that, you just take, like implicit differentiation, you take the derivative with respect to time of each of the components of that vector. That's all you do. And then if you want to do acceleration, same sort of thing, you take the derivative of the velocity vector. Notation is r with a double dot, second derivative with respect to time. Take the second derivative of the position vector for each component with respect to time. So now we've got extending our calculus into 3 dimensions for studying kinematics. Okay, and the same works going back. So if we're given a velocity vector function, we can take the antiderivative to work out the position. And taking the antiderivative, you just take the antiderivative of each component, the I, the j, and the k component with respect to time. If you're wanting to work out the velocity from an acceleration position vector, an acceleration vector, you can take the antiderivative of that with respect to time, and you can just simply split it up and take the antiderivative for the I separately with respect to time, the j and the k. Actually, that should be 2, shouldn't it? Yes, that's right. So, okay. So, yes, that is also correct notation. So you could actually say r dash of t, that's equivalent, or r double dash of t for acceleration here. Or you can have v of t as a vector. There's a little tilde underneath it. You've got to have little tildes underneath. Or a, denoting it's now a vector quantity with a little tilde underneath. Otherwise, it's a scalar quantity in one-dimensional motion, one-dimension kinematic motion. So you need to note that. That's why it's important to start putting those tildes underneath when you have vector quantities. Okay, so here's another example. Okay, so we've got a particle travelling on a path described by the vector equation r as a function of t, 2 cos t is the I component, and 3 sine of t is the j component. Sketch the path of the particle, find the velocity equation for this object, find the acceleration vector equation for this object. So sketching the path of the particle, what do you think you might do? How would you sketch the path of the particle? What do you think? Yep, Harry, you're right. Convert it to Cartesian form first. Yep, on the x and y axis. So you equate the x to the I component and the y to the j component. Okay. Now this one requires a little bit of manipulation. You can see because it's got a cosine and a sine, if you manipulate this slightly, you'll be able to apply the Pythagorean identity to relate those two x and y together. If you divide the x, the x, both sides by 2, you get x on 2 equals cosine of t. And for the y, if you divide both sides by 3, you get y on 3 equals sine of t. And then you can combine those two x and y, and it forms an ellipse. So this path is an elliptical path, and the other thing we need to know, what else do we need to know? We're going to sketch the path. What else do we need to know? We know where its path, but what else informs a person looking at this object? Direction and starting point, exactly. So we need to substitute t equals 0 to get the starting point, and maybe another value of t that's very simple to evaluate, like pi on 4 or pi on 3, something we know exact values for, stick it in and we can work out a second point. So we've got the path, all we need is a starting point and another point to work out the direction. So this is going to start here at 2, 0. Okay, and it's going to go up in this direction. So we've got a starting position at t equals 0. If we just substitute t equals 0 into the vector equation, we'll get that starting position. And if we substitute t equals pi on 2, that'll give us this position up here, and that'll inform us of the direction of the motion of this object on this path. So putting in pi on 2, let's just do that. For that one, r of pi on 2, that's going to be 2 cos pi on 2i plus 3 sine pi on 2j, which is going to give us, this point up here, which is 0, 3. So we know the starting point and we know the direction is going to be anti-clockwise for this object. And when we're sketching this, we need to show the arrow on the path showing the direction of motion, and we also need to say the starting position. And you can do that by either saying starting position or t equals 0. Pretty much starting position. Okay, so now we want to work out the vector equation for the velocity for this particular object. Now, velocity is the derivative with respect to time of position. So what we need to do is take the derivative of each of the components here. So take the derivative of each vector component. So the x component with respect to t is going to be -2 sine of t. And the y component, the derivative of that with respect to t is going to be 3 cosine of t. Putting that all together, we're going to get a vector representing the velocity of this object now moving around on that path. So we've got the path and we've also got the velocity. So we can work out things about the velocity now too. If we're asked questions about what is the velocity at t equals 0, we just substitute it into this equation and we can work out the velocity at t equals 0. What is the velocity at t equals 0? -2 sine of 0, well that's pretty much going to be 0. 3 cosine of 0, that's going to be 3. So this is now defining the vector representing the velocity of this object. So at this point here, we're at t equals 0, this object is moving at 3 units per time interval, 3 units per second or whatever, in the j direction, straight up here. That sort of makes sense. Right at that very instant. Okay. Alright, so we're asked to work out the acceleration as well. So the acceleration, we just take the derivative of the velocity with respect to time. So we take, this is showing the second derivative position, which is the same as dv dt. This is dv dt, which is the second derivative of position with respect to time. So we're going to get another equation here, take the derivative, we just did that up there. For the j component, take the derivative again with respect to time, and this equation represents the acceleration. So again, we can work out the acceleration at t equals 0. It's going to be -2 I plus or minus 0j. So the acceleration is going in the negative direction. And that makes sense because look at the direction of the motion of the object. The acceleration is towards the origin as a vector quantity. It's like that way. But the velocity is up this way at that instant. Okay? Kind of makes sense. Because remember, the acceleration is going to modify the velocity anyway, as we're going along. Alright, so more on projectile motion. Now, projectile motion, we're going to use those vector equations and the calculus to determine how an object is travelling under the influence of gravity, basically, in 3 dimensions. So, what is a projectile? A projectile is something that flies through the air, I guess. But mathematically speaking, it has horizontal and vertical components of velocity and displacement and acceleration as well. So there's vectors that we can use to define a projectile's motion. When a projectile, an object, is launched, it has some initial velocity components and some initial position components and some initial acceleration components. So we're going to look at some examples of some problems now. So when we have a projectile, it's under the influence of gravity, it behaves under the force of gravity, and so, anything, what goes up must come down. whatever. So a projectile, once projected or dropped, continues in its motion by its own inertia. What does that mean? Do you know? Anyone do physics? It will continue at the same velocity unless a force acts on it. Okay, so the gravitational force acting on an object is only acting in a downward direction. When this object is a cannonball, I suppose, this object is initially launched with a horizontal velocity. And over time, as it falls to the earth, the horizontal velocity supposedly remains the same. The only thing that's changing is the vertical component of the velocity under the influence of gravity. That's the idea. Have you studied this in physics? Do you do physics? Who does physics? Who doesn't do physics? You did it in year 11. So this is the position of the cannonball at various points in time. Okay, so at t equals 0 it's here, and then keeps on moving through space until it hits the ground, at which point it stops moving. Okay, at t equals x, whatever, it stops moving. But the whole time it's moving, supposedly there's no air resistance, so the horizontal velocity remains constant the whole time, and the only thing that's changing is the vertical velocity. Let's think about that. Okay, so you can kick a football, okay, and you can have a velocity, an initial velocity you kick the football with. That's a vector, right? It's got a magnitude and a direction, and you can decompose that into x and y components, whatever your reference is, I and j components, x and y coordinates. Okay, so you have an angle of launch relative to the I direction and relative to the j direction. So if this is your velocity vector, you can decompose it into I and j components. Because the horizontal component will remain constant throughout the motion, the projectile motion of this object, but the vertical component will be modified under the if I could draw a straight line, that's hilarious, that's a terrible line. Under the vertical component will change under the influence of gravity. So the vertical component will be influenced by gravity. So even though this is the initial launching velocity, over time it will follow, it will succumb to gravity and start going back to the earth. Unless you're a really good kicker and you can launch your football into space, escape the Earth's gravitational field. Okay, so what do I mean by all this? We've got these vector components of velocity. So it's got magnitude and direction. So for example, if you launched a javelin at 50 meters per second at an angle of 60 degrees from the horizon, the x component of that would be 25 meters per second, and the y component of this would be 43 meters per second, worked out using this angle here. Okay, the angle of 60 degrees. The x component is 50 cosine of 60, that's that length there, and the y component is 50 of sine of 60. Turning that into a vector, this velocity vector is 25I plus 25 root 3j. That is defining the velocity vector of launch of this object, this javelin. Okay, so we need to see more examples of this. So the horizontal motion of a projectile is influenced by the initial x component of the velocity. That's the initial x component. And it travels in a horizontal motion, not affected at all by gravity. So you can work out at a certain point in time what is the displacement of this object. but it's not going to travel for an infinite amount of time in the horizontal direction, because what's going to happen is the vertical component will come under the influence of gravity. For here, AX is equal to 0, but the vertical component, AY, is equal to negative 9.8, which is the gravity, acceleration due to gravity, meters per second squared. So this vertical motion will cease at some time. So at some time, t equals some time, this thing will stop moving. Velocity will be equal to 0. Oops. The velocity will be equal to 0. Velocity y was going to be equal to 0 at some point in time. At that point in time, we can also determine what is the horizontal displacement and what is the vertical displacement of that object by substituting it into that time equation. Does that make sense? I hope it does, because we're about to do an example. Does that make sense? Any questions? Shall I keep going? Because I have an example. Back to that cannonball. Okay, so if we launch that cannonball with a vertical velocity of 20 meters per second. So this is at this is the velocity. You said that velocity is going to be 20I. Right? That's the velocity of the initial launching velocity of this particular cannonball. So what's going to happen? The horizontal component is going to remain the same, because the only force acting on this object is the downward force of gravity. So the vertical component every second is going to increase by negative 9 or decrease by negative 9.8 meters per second. That's what the acceleration is going to do. So after 1 second, the vertical velocity is negative 9.8 meters per second. The horizontal velocity is still the same, 20 meters per second. So at 1, this vector, velocity vector, looks like 20I minus 9.8J. At t equals 2, you can see the velocity, the vertical velocity, has decreased by another 9.8 units. So at t equals 2, the velocity vector still has that horizontal component of 20I, but the vertical component is now negative 19.6. And this is all meters per second. That makes sense? And see, it keeps on increasing every second. That vertical component is decreasing by 9.8 units, but the horizontal component remains the same. So we can see that the horizontal component is remaining constant, but the vertical component of the velocity is decreasing by 9.8 meters per second every second due to acceleration. Gravity. Okay, so here's another little example here. A boy throws a ball in the air. The horizontal component of his initial launching velocity is 12 meters per second, and the vertical component is 19.6 meters per second. Okay, so that as a vector, that's the resultant vector. If I could draw it in a straight line, that's the resultant vector. He's thrown it in that direction, decomposing it into the I and j components. So after 1 second, this is at t equals 0. At 1 second, t equals 1, you can see the horizontal components remain the same, but the vertical components decreased by 9.8 meters per second. And then at t equals 2, the vertical component is 0. The horizontal component remains 12 meters per second. And then after at that point, the object starts going downwards. Still travelling horizontally 12 meters per second, but its downward velocity under the influence of gravity is now, this is at t equals 3, is negative 9.8 meters per second, and at t equals 4, till it eventually it's going to come to a grinding halt when it hits the ground, whatever time that might be. Okay, so you can see that. The horizontal velocity, that's the whole point, is remaining constant, but the vertical velocity is being influenced by gravity. That's what projectiles are. Under the influence of gravity. Assume no air resistance for affecting the horizontal velocity. Okay, so what's happening to the displacement in this time? So, okay, we've got the displacement happening here. So, okay, using that equation, S equals ut plus a half a t squared, we can work out the displacement of the object in both the horizontal and vertical directions. We're just substituting the various times in there, and remember a is negative, for the vertical component, for the vertical ay, whatever, is negative 9.8 meters per second squared, that's the acceleration. For the horizontal component of the acceleration, that's 0. So it's remaining at a constant velocity for in the horizontal direction. So that means the horizontal displacement can just be, just plug it in here, the time you know the thing is airborne for, you can work out the horizontal displacement, but working out the time it's airborne for requires you to work out components of the vertical displacement. When it hits the ground, it's obviously going to stop. When is that going to happen? So this is the cannonball, I think. I don't know. Is it the cannonball? So the cannonball has this motion here as it's being launched. Alright. Okay, so what we need to do. Typical problems. We need to determine the time of flight. We need to determine the horizontal displacement, and we need to determine the peak height. These are typical problems, but there might be some outside this. So I've got an example here. So we've got a footballer. Do you know who that is? He's kicking a football, I don't even know if it's physically possible, from a height of 0.3 metres, the initial velocity of 25 metres per second at an angle of 45 degrees with the horizontal. So we're going to determine the time of flight, the horizontal displacement, and the maximum height of the football. Anyone who knows who that is? Who's that? Do you know who that is? Anyone know? Anyone know their football history? No, don't worry about it. Okay, let's work it out. So this is a diagram that's going to help us work out what's going on here. So this is the initial velocity of launch of the football at an angle of 45 degrees with the horizontal. So looking at this, just drawing a little diagram, a quick little triangle here, right angle triangle, we can work out the vertical component of velocity, the horizontal component of velocity and the vertical component of the velocity here, for this initial velocity. This is going to help us. Okay, so this, we know some things. We know the initial velocity from drawing this little quick diagram, and we also know the acceleration vector. The acceleration acting on this football, it's only going to experience acceleration due to gravity, which is negative 9.8 in the j direction, going down, back towards the Earth. That's the j direction, point of reference, right? Meters per second squared. So this is the acceleration vector equation. And this is the initial velocity vector equation. There's the I and j components of the initial velocity at t equals 0. That's the initial velocity. Okay, so we're going to put this all together now. So we can work out by using calculus that the velocity vector with respect to time is the antiderivative of the acceleration vector with respect to time. So this is the equation we're going to get. If we take the antiderivative of the acceleration, that's just going to give us negative 9.8 t component for the velocity in the j direction plus some constant. How am I going to evaluate this constant now, guys? Do you know? What information do I have to evaluate the constant? Yes, we have information at t equals 0. So we have this now, this is our velocity vector, right? With respect to time, by taking the antiderivative of the acceleration vector. Now at t equals 0, we have an initial condition. So substituting that in, we can, at t equals 0, we've got c is equal to the initial velocity vector. And it's been incorporated here. So there's the I component, 25 cosine of 45, and this is the j component, 25 sine of 45 degrees minus 9.8 t in the j direction. Can you see what I've done here? This is now the velocity equation, vector equation for the motion of that football under the influence of gravity. Can you see it's got a horizontal velocity component and a vertical velocity component affected by time? Can you see that? Hopefully that makes sense, because that's going to help us work out now the time of flight, the horizontal displacement, and the maximum height of the football. Right, so this is now our velocity equation. We can actually simplify. Cosine of 45 is 1 on root 2, so that's the velocity equation. And sine of 45 degrees in exact values is 1 on root 2. So this is our velocity equation now. We have a acceleration equation and a velocity equation, vector equation with respect to time. Right. So we need a position. Position vector can be worked out by taking the antiderivative of the velocity vector with respect to time. So we take the antiderivative of each of the components, I and the j component, with respect to time. So we're going to get as our position, taking the antiderivative of 25 on root 2, the antiderivative of that is 25 on root 2 times t. That's the I component, and the j component with respect to time, that has a t in it here. So that's going to be 25 on root 2 t here, and then minus 4.9 t squared. Can you see where this comes from? J, that's the j component, plus this constant of acceleration. Now we know some things, because at t equals 0, the football was kicked from a height of 0.3 meters. So we know where this position here, where it was. That was at t equals 0. That was at 0.3 from the ground. Okay, so there's the ground here. Blech. Whatever. That was just above. So this is in the j direction. This is position, so we can use that. This is like another initial condition to evaluate that constant. So just putting that in. So this is now the position equation with the constant evaluated to be 0.3j. So we have a acceleration equation, a velocity equation, and a position equation, all vector equations, all with respect to t. Each component is a function of t, time. And time must be greater than or equal to 0. Let's keep on going. So we've got all that information, and hopefully that all made sense, how to derive all of that by taking the antiderivative and substituting initial conditions in there to work out those constants of integration. So now we need to work out the time of flight. The time of flight, the vertical component, we want to work out when is that ball back on the ground. When is the J component equal to 0? That's the J component. When is the J component equal to 0? So we need to take the J component of the position equation, it's this bit. When is that equal to 0? That signifies this ball is on the ground. Does that make sense? When is that equal to 0? That is equal to 0 solving for t at t equals 3.63 seconds. So now I know the time of flight. This ball is launched and it takes 3.63 seconds to hit the ground again. Now I can use that to work out a lot of other things. I can use it to work out the horizontal displacement. How do you think I might work out the horizontal displacement? How do we work out the displacement of something? Constant motion equations. Yep, so the velocity of this thing in the horizontal is a constant value. It's 25 on root 2. Now it's going to travel at this horizontal component for 3.63 seconds. So we're going to be able to work out the displacement by just multiplying the velocity by the time for the horizontal component. Works out to be 64.17 meters in the horizontal. Is that a good kick? I wouldn't know. That seems like a very long way to me. It's possibly not even possible. I don't know. Can anyone kick over 60 meters? I don't know. Put my hands up. I don't know. I just make up the question. Yeah, it's decent. Okay. So what's the next question? The maximum height of the football. Okay. How do you think you might work out the maximum height of a football? We've got the horizontal displacement. How high is it going to actually go? When the velocity is equal to 0. But hang on, look at the velocity. It's got I and J components. Which bit's going to be equal to 0? No. This is the velocity equation here. When the J component of that velocity is equal to 0, it will no longer be going up anymore. It will start to come down. And at that point when it's 0, it's reached its highest point. So when the vertical velocity component is equal to 0, that's the vertical velocity, that's when it's going to reach the highest point, and thereafter the velocity will start to become negative, going back down towards the Earth. So solving this one gives t equals 1.8 seconds. So then we can sub that to work out, if we sub this into the vertical position component, okay, we can sub that t is equal to 1.8 into the vertical component of the position vector. We can work out how high this thing actually travelled. So subbing that in, this thing travelled 16.24 metres in height. That's the highest point it got to, that football. It's a pretty good kick, I don't know. So, yeah. So hopefully you understood that example. That's a typical kind of example, using the acceleration, velocity and position equations for a projectile. So what actually happens? If you think about this launching angle, it affects things, right? A steep angle means the vertical component is much larger. So it means a high trajectory, but it doesn't go as far. The same ball kicked with a shallower angle, okay, has a smaller vertical velocity and a larger horizontal velocity, so this ball maybe will travel a greater distance. I don't know. Certainly won't go as high as the first one. So a ball launched at a steep angle will have a large vertical velocity and a small horizontal velocity, and a ball launched at a low angle will have a large horizontal velocity component and a small vertical one. And that's the end of my video. So thank you. Let me just stop sharing this, stop my